Someone have a piece of paper?
What piece of paper? Like a leaf? Loose leaf?
Yeah.
Why would I like your haircut?
No, it's not funny.
Makes you feel like you're in the army again. You don't understand how much I hate Please pass the class roll around. Okay, half-pass the towels.
Wait, someone don't say anything on YouTube.
Yeah.
Wait.
The key is posted. Please learn from your mistakes. Large number of A's. Good job on that. Test 4 will probably be a little bit more difficult. A lot more new functional groups, acetals, imines, enamines, etc. The chemistry is not as straightforward. It's more nuanced. The products will look a little odd. You've got to think mechanistically. Think mechanistically, you'll be fine. There's some memorization. You've got to know what an enamine is. Start from there, etc. The memorization gets you going, but then your mechanistic knowledge needs to kick in and your understanding. Okay, acetals. We can react an aldehyde or ketone with two equivalents of an alcohol, really two OH groups. We can replace this oxygen with the two oxygens from here. The carbonyl oxygen is lost as water, acetal, functional group. This is the true equilibrium. We showed the mechanism last time. Every reaction step is completely reversible. That is, we are under Roman numeral 2. Everything's reversible. If this reverses, what will you get back? You'll be able to show that. Okay? Basically, these are replaced with the oxygen. You get the double bond. Mechanistic, we just go backwards. That is, protonate one of these oxygens. And then the other lone pair kicks it off. And then you're just going backwards. Do the mechanism backwards. This is the true equilibrium. How would you drive it this way? One way is remove the water as it's formed. How can you remove the water?
Boil it.
How would you remove the water?
There's different boiling points and you just abuse that.
How would you remove the water?
Do you add sodium and hydrogen?
You could add a drying agent to help maybe dry it up. Once it adheres to the drying agent, it's then removed from the equilibrium.
Will the water separate out, like in terms of density?
Well, in this particular case, ethanol is probably used as solvent. You could. One common way is to distill it out. As it's formed, distill it out. In this particular case, the problem is the boiling point is 100 degrees. Boiling point of ethanol is about 80 degrees. If you try to distill this out as it's formed, the ethanol is going to distill out of your reaction flask first. So that's not going to work. What's another way to drive this equilibrium instead of removing water?
Just add another ethanol.
Yeah. In practice, you use excess to drive the equilibrium. Then at the end, you just remove the ethanol on the roundabout, the extra. And by the way, when you remove the ethanol on the roundabout, it may remove the water too as an azeotrope. But we can use that. You don't want to use excess this because then you're going to be left with this. We're looking to drive this to completion. Use excess of this and then get rid of that at the end. But because of this boiling point problem, we'll go to the next reaction. That is, it's actually more common to make cyclic acetals. That is an acetal, right? It's a carbon with two oxygens. Each oxygen has R groups. This happens to be cyclic. Okay? Very common to make cyclic acetals using a diol. This is your true equivalence of the OH. but it's within one molecule, so it's a diol. Here's your H plus catalyst. Variety of catalysts can be used. Mechanistically, we can protonate carbonyl, yeah. And one of the OHs adds electrons up. We get, boom. I'll draw the methyl down. Got this. Boom, boom. 2 carbons between there. This here. So we get to this, right? That's just a simple addition. If we lose that proton back to catalyst, what's that structure called right here? Half acetal? Okay, but we want to get the full acetal. Proton transfer. So we can get water to be the leaving group. Hold on, that's not right. The OH is here. This has the oxygen, and then we got boom, boom, boom. Okay, gotta be careful. You might want to bring this in. No, that's a tertiary carbon. No. But these electrons right here, boom, make pi bond kick off leaving group. And we got what? Oxygen here, but this oxygen has boom, boom, boom on it, right? We lost the water, but now look, now these electrons can come here, kick that onto that oxygen, and we're getting to where we want to go. We got boom, boom. We now have oxygen, boom, boom, boom. Made that bond, there's still an H there, right? There it is, we just got to give up the proton to whatever gave it up over here. What do we got? Paratyrene sulfonate, take the H. A lot of you are leaving this arrow off of your mechanism. These electrons then move on to oxygen, you need to show that. That gives that and the reformed catalyst, right? So the diol has the 2 OH groups, but it's connected, so you get the ring, and everybody's happy. Cyclic. Ooh, plus water, right? Boiling point of 100 degrees. Here, because it's the diol, it's a much higher boiling point. Boiling point's about 198 degrees. Here, you can do this reaction at like 150 degrees, or 120. As the water's formed, it'll boil out, but this is not going to boil out. Much higher boiling point. It's much more convenient here because this is much higher. You end up with a cyclic. But the cyclic acetals are very common, probably because of that reason right there. Make sense? Use a higher boiling starting material, then you can distill the water out. Cyclic acetals, these 5 and 6 member rings tend to be your best size there. Okay, acetals tend to be end products. They tend to be a little unstable because they will revert back if you treat them with water and acid. That is, how would you drive the equilibrium back this way? Instead of removing water, you would add lots of water and acid. Protonate, you're going to get that water coming in and you're going to go backwards in that mechanism. What are acetals good for? Huh?
Protecting you?
Acetals are often used as what we call protecting groups. To protect a carbonyl. We know carbonyls are prone to being attacked by nucleophiles. What if you don't want the carbonyl to be attacked by a nucleophile? You can protect it. For example, what if you want to treat this compound with LAH and you only want to reduce the esters? Boom, boom, make aldehyde and come in again, you're going to end up with this. What if you wanted to make this compound? The problem is, it ain't going to just react with the ester. It's going to react over here as well. You're not going to be able to, and actually this is more reactive because this has a donating group. Try to react this with LAH, this is the product you're going to have to get here. But we can protect this over here by making acetal. We got this diol, we got an acid catalyst, and this is going to give acetal. It'd be a 6-membered ring because we've got 3 carbons. Yeah? We can make acetal. Now we can come in here with LAH and we can get this here. Double addition to carbonyl, we end up with alcohol, 2 new H's here. Now, can we remove the acetal and reform carbonyl? Sure, that's a reversible functional group, okay? And if we do that, we can get carbonyl back here. How would we do that? What reagent? What would you treat it with? We just said this 2 minutes ago.
Water. Yeah.
Water plus what? Plus acid catalyst. And a lot of times this is written how? H3O plus, right? Mechanism will be just the reverse of our acetal mechanism, but because there's lots of water, it'll go reverse. You need to look at the mechanism in reverse. And we would regenerate the carbonyl compound plus the diol, it'll come out too. It's a true equilibrium. See, once we make the acetal, it's no longer electrophilic. A nucleophile is not going to react here. No longer electrophilic. We have protected the carbonyl, and then we deprotected. Deprotect and reform. That's how we can make A. By protecting the carbonyl. Acetals are common protecting groups. I'll bet you a hamburger that you look on Wikipedia and type in protecting groups, you'll get a big hit and you'll find acetals there. It'll probably give you protecting groups for different functional groups. Acetal is a common protecting group of aldehydes ketones. Acetals can also be protecting groups for diols, because the diol is the other starting material to make the acetal. For example, if you have this diol, it's a diphenol. If you want to make Grignard over here, problem is this Grignard is no good. You cannot make this Grignard, because as soon as you make it, it's dead. As soon as you make it, proton is going to transfer here. This is a carbanion essentially. The proton is going to transfer there. You're going to end up with H here and anion here. So you can't make this and say, okay, H's, don't do anything. It ain't going to listen to you. So you effectively cannot do that. But guess what? What if we made acetal here? It's a diol. How would you make acetal? Well, we need a carbonyl compound. Now, it really doesn't matter because that's just going to be sort of used and then taken back off. What if we used acetone? So given acetal, can you show the acetal that it would give? 2 OHs and a carbonyl. Used to be a song, two turntables and a microphone. Something like that. Okay. 2 OHs and a carbonyl. Okay, acetal. What we're going to have here?
Yeah, there you go.
It's going to be that there because there's your acetone, but instead of carbonyl, the two oxygens have replaced the carbonyl. Look at the mechanism. Do the mechanism. That's an acetal right here. That can be made. You get this plus what?
Water.
Plus water. That oxygen is now released as water. Do the mechanism. But the acetal, the OHs are effectively gone now. The acidic H's. Now you can do Grignard. And you're off to the races. If we want to make this compound here, you can't do this because this is no good. If we want to make that compound, let's just do one step. We get our Grignard. Then we can come in here with just simple epoxide, essentially an anion, right? Anion taxir opens that up, and we end up with nucleophile carbon-carbon OH. It's going to get protonated with workup, right? We get that. We'll test one chemistry. And then, if we want to liberate the two OHs, what do we treat this with? H3O plus, deprotect it, and we liberate the diol. You're also going to liberate acetone, but that's probably going to go in the waste container, because here the main functional group is your diol. By the way, when you make an acetal from acetone, it's typically called an acetonide. Now, I don't like that name because "ide" sounds like an anion, like bromide, chloride. So it's not a good name. But an acetonide is typically an acetal that comes from using acetone. And if you look on the white handout, the one you printed yourself, on the very first page, there's a drug. It's an ointment, actually an ointment. I got some in my medicine cabinet. It's called triamcinolone acetonide. Please take a look at that warm-up question. So acetals can be used as protecting groups, both for carbonyls but also for diols. Questions about the chemistry? What's down here? Structure of sugars. Well, I showed you the acetonide. Sugars. White handout. You'll see lots of sugars in biochemistry, aka carbohydrates. Carbohydrates, standard carbohydrates can exist in two forms, sort of the open form and then the cyclic form. Here's the open form. Open form typically shown as Fischer protections because you have multiple chiral carbons. Depending on the stereochemistry here, they have different names. Glucose has certain here. But it can also exist in this cyclic form. And cyclic form shown here in a chair conformation. Ever heard these things?
Yeah.
How do you get the cyclic form? One of the OHs attacks the carbonyl. Here's a carbonyl. And it's actually this OH attacking this carbonyl. 1, 2, 3, 4, 5. That's not right. No, this structure is wrong. It's missing an OH. Missing an OH there. Shame on that. 1, 2, 3, 4, 5, 6. This OH attacks carbonyl. 6-membered ring right here. Attack carbonyl. Now here they're showing very generically they also lost their OH there. Somebody had a bad day here. But the new OH, okay, that's formed can either be equatorial or axial. Okay? And depending on whether this OH here is equatorial or axial, it's called alpha or beta. Where's that mentioned there? I thought it was listed here on the side. Yeah, they could be called alpha or beta depending on how that's the OH is. Now, actually, this is a little bit overly generic. Pretend there's an OH here. That's an OH. What is this carbon functional group here? Well, it's a hemiacetal. Because you got a carbon with an OH and an OR. Okay? So the cyclic form of your sugars are actually hemiacetals, half acetals. And it's in equilibrium closed and open because, well, can't this reverse? Can an acetal or a hemiacetal go back to the carbonyl? Yeah. I mean, these electrons just come in here and kick that oxygen back off. If you have a proton, you can protonate that oxygen first. So it goes back and forth. So I think it shows the same thing down here. Yeah, here are the two forms. Here it shows the OH down, that's the alpha form. And here it shows the OH equatorial, that's the beta form. They're both D-glucose. They're all in equilibrium, so you have all these forms that are possible, all in equilibrium. So, carbohydrate chemistry. Sweet stuff.
I get it.
Okay, let's see where we're at.
Trigger.
Okay, what if we react to carbonyl with an amine? Instead of alcohols, what about an amine? Amine. Number 2, one must have been acetals. Yeah. And we're under B, which is loss of water. Okay. So we're going to lose water. This helps keep me organized. Hopefully it helps keep me organized too. So we can react an aldehyde or ketone with an amine. The simplest amine will be ammonia. We can include an H+ catalyst, although we'll have to talk about that. And we can get an imine. And of course this oxygen is now this oxygen is losing water. And what is an imine? Carbon double bond N. Carbonyl is a C double bond O, and imine is a C double bond N. So it's analogous to a carbonyl.
We have like an acid and a base. Why do they not just?
That's why I said we might have to address that. Yeah. You're right, we got an acid and a base. Is that compatible? Well, to a degree, and everything's in equilibrium. And how much acid are we talking about? Full equivalent is not going to be good.
Yeah.
But what about one molecule of acid?
I don't get it started. That's what I was thinking. So next week.
Okay? We'll talk about that. We'll mention it again. Now, if we use a primary amine, We're going to have a methyl on the nitrogen. The water comes from here and 2 H's from the nitrogen. We don't lose the methyl. Imines. Imines can have R groups because the nitrogen is trivalent. Okay. Now, yes, you can actually make imines without an H plus catalyst, like you did in lab. You didn't use an H plus catalyst. It's traditionally used in the textbook. You don't have to. We'll use it here. Since we're going to use it, let's protonate the carbonyl first, right? I mean, the mechanism should be just start doing it, and you will find you just work your way there. There's nothing really new here. Nucleophile in, electrons up. Boom, 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 boom. You want to do it with methylamine? Let's do it with methylamine, so we'll keep that methyl there. We got a methyl. It's a positive charge, right? What do you want to do next? Proton transfer to the OH. Boom, boom, boom. I'm going to draw the methyl down. Leave the lone pair behind. And now we got the proton on the oxygen lone pair. Now these electrons can come in here and kick off the water. You get the double bond in with methyl there, but there's also an H there, yeah. Positive charge. There we made the water. How do we get final product? Whatever gave up the acid, what's your favorite acid catalyst? H2SO4, so we got HSO4 minus. This can take the H, these electrons stay behind. We get that, and we reform our acid catalyst.
Would it be wrong to do a concerted step between the HSO4 minus and then the resonance kicking off the water?
You here?
Yes.
I would do it like this.
Okay.
Because you're saying you want the sulfuric acid to come in here. Okay? Look at this though in terms of rate. This was H plus transfer. I mean, that's a mechanistic step. As soon as we form this. Okay, let's say it's formed now. Okay? You want this to come here? Well, while this is making its way here, guess what? This has already happened. Why? Because the electron's right here. It don't have to do anything. It's just, okay? This takes time to come in here. This is going to happen first because it doesn't have to wait for that sulfuric acid to come. So that's why I would do it. It's just, this is more traditionally done this way. Also, I would never use this as a base unless something really looked like an acid proton. Now it looks like an acid proton on this positive nitrogen. There we go. Traditionally, you would say, how do you drive this reaction? You can remove water. Okay. When you made amine in lab, did you have to remove water? How did you do it? You took your aminofluorine, that was your amine, and you reacted it with what? An aldehyde. Okay? And you made an amine plus water. Did you have to worry about driving it? Did we remove the water by distillation or anything? No. Traditionally, you might have to, but the reason you didn't have to in the lab is because the amine you made something like this. Here's your imine. Came from the nitrogen attacking the aldehyde, and double bond carbon. and double bond carbon. You replace the methyl with the fluorine big old ring, and you replace, that's got 2 R groups on the carbon. Here you actually have one of them as an H, right? You see the aldehyde there under my hand? If it was an oxygen, it would be the aldehyde. But the amine replaced the oxygen, and now we have that there. Okay. The reason you didn't have to drive it by removing the water is because it's self-driven. It's self-driven because it's conjugated. You see the conjugation here? It's all conjugated. This double bond is conjugated here. You're making a highly conjugated system. Because of that, it just drives itself. It's so favorable. That's why you don't need it. So there can be other reasons why a product is driven other than the generic reaction. That's an imine. Imines are very versatile, very versatile. We'll see imines a lot in the next couple of pages. Show 2 products here. You guys on the right, over here, to the first one. You guys over there, to the next one. What are you going to put on your note card? Let's see. Aldehyde ketone and amine. What does that give? Imine. With loss of, the oxygen is lost as water. Imine is also known as a what? We've said it in lab. We said it here on Wednesday. It's written on the very front of the yellow sheet. Shift base. Shift. Oh, biochemistry, you will call it means shift bases. Because the nitrogen lone pair is a little bit basic, and your body uses that as a base. Okay, product here. You can show this 2 different ways. I'll do it like this to reinforce the fact that, hey, if I draw an oxygen, that's that. But guess what? It's now nitrogen. And guess what? There's a benzyl group on there. So there's your product. The nitrogen replaced the oxygen. Right? Isn't that what an imine is?
Yeah.
The amine replaces the oxygen. The oxygen is lost as water. Same question.
So would you assume that there could be H plus catalyst?
I'm not showing the H plus catalyst. Let me also go back. Marvin indicated here. Yes, a lot of books will talk about this. Seems to be something books like to talk about. Yes, H plus catalyst is often shown. Problem is, if you use too much catalyst, it will actually slow it down. Why? If you use too much, those reactions get slow. And actually, if you use way too much, your reaction won't happen at all, Marvin. What?
Because if you use a lot, you start reducing the ammonia, which is one of your reagents, which drives the reaction.
Yeah, you want enough to sort of protonate, but you don't want enough to tie up your ammonia, because ammonia will react with it. Then you're like, well, if I add any, won't it react with the ammonia? Yeah, but it's in equilibrium. One's a weak base. So there's an equilibrium between ammonia and H+. But studies have shown if you use too much catalyst, it'll actually slow it down because it starts reacting too much with the ammonia. There's a sweet spot of how much catalyst. Okay? Again, you can make imines without catalyst. In lab, when you made your imine, did you use H+? No, you did not. So yes, you could show one here. I didn't show it. Product down here. I'm going to replace that oxygen here, and I've got what? Boom, boom, boom. By the way, one of those imines has isomer possible. Stereo isomer. Which one has a stereo isomer possible? Yes, this one actually has stereoisomer possible because we could have the benzyl group over here. This is like an alkene. It's a double bond. It doesn't have free rotation. E and Z. You can do E and Z just like this. High priority group here is the benzyl here. So what is this? E. Is this same side?
What's this?
Yeah. And actually, the imine you made in lab has stereoisomers possible, and that's why when you're in the TLC of your imine, it usually shows two spots real close together. I think that was the two isomers, E and Z. Does this guy down here have E and Z possible? No. If you put this group over here, it's the same thing.
Yep.
Because there's nothing here. There's no difference. You can have stereoisomers of imines just like alkenes. Stereogenic. Yes, an imine doesn't have to be. It can be, just like alkene. What's next?
M&M.
It's an enemy. Anemone.
What if we use a secondary amine? Oxygen. It doesn't have two H's to lose. How are we going to make water?
I agree.
If you use a secondary amine, you don't get an imine. What you get is an enamine. Enamine. What is an enamine? Ene, which is like alkene. There's your ene. It's an ene with an amine. Alkene that has an amine bonded to it. Called an enamine. What do you call an ene that has an alcohol bonded to it? An enol.
Yeah,
Right?
That's what you said last week.
Yeah, it's like what Donkey says, enol. This is an enamine. How do you get enamine? I'm going to take us up to a point. I'm using H plus catalyst. What we got here? We got an H. We're actually going to have two methyls here. Actually going to have two methyls. You should be able to make it up to this point. At this point, we're going to kick off the water. Double bond with two methyls. Positive charge. Previously, same mechanism as before, except before we had another H at this point. And we lost the H to give our imine. But here, because we started with a secondary amine, there's no H left at this point. So how are we going to lose the other H? Where does it come from? Well, there's two here. There's only one there. It actually comes from here. Now, you can get there two different ways. Oh, it forms a double bond. Why don't we do resonance? And by the way, some of you, this is called a resonance arrow. Whenever you're converting between two resonance structures, this is the appropriate arrow. Resonance. That is that's just like a carbonyl that was protonated. Let's give the nitrogen what it wants. Let's just move electrons. And that gives what? Gives that. And what's here? Positive. Because look, doesn't the final product have nitrogen with a lone pair and it's neutral? Yeah. Resonance gives us that. Now, we got two H's here. How can we go neutral?
Times the base takes one of the electrons to tell.
Yeah, maybe we use HCl. Cl minus takes the H, the electrons move in. What does that do? There you go. So we lose an H from a carbon instead. There's none on nitrogen to lose. Question?
Couldn't the Cl minus take a cation? Couldn't the Cl minus take a cation?
Attack the cation? We've never really done, oh, you mean here? Oh, I thought you meant nitrogen content. It could. Okay, let's say it did. Boom, 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 boom. Give that type of product? It's not going to be a stable product. Why? Because anytime you can make a kick off a lone pair, it's just not going to be, you're not going to usually see products like that. And when that does that, you get back here, which is essentially the same as this, because these are resonance groups. There's certain products with two things on one carbon where it's not going to be. What does this look like when this takes an H and puts in the double bond? This looks like the last step of what? It looks like the second step of an E1 elimination. E1 elimination, you leaving group leaves, cation, and then you do the fast beta elimination. Yeah. You get an enamine because there's no H to lose from nitrogen, you lose it from carbon. How do we know we get this? Well, it's been proven, trust me. Here's our mechanism. Anybody got a better one? So no, it's been proven. Here's our best mechanistic theory. That's where we're at. Enamines. Enamines. Come from the secondary amine. Tertiary amine doesn't give any product. Tertiary amine is not going to give a product. You're not going to be able to isolate something from that. Enamines. What about stereoisomers here? The alkene, you can have stereoisomers of the alkene. Is this alkene E or Z?
Z.
Nitrogen, carbon, what is that, Z? Yeah, it could also be E. Enamine could also be E.
Thanks.
Actually, E may be more favored because the bigger groups would be more trans. I do it like this. What about regioisomers? Someone show a regioisomer that's possibly formed instead of the one I showed. Instead of the one I showed, you might think back to E1. E1 elimination can give different alkenes. Yeah? What about H's over here? What about the base taking this H and these moving in? What would that give? Well, let's show what that would give, and then maybe let's give it a name. I give double bond over here, right? What functional group is this? It's an ene with an amine. What do you want to call it? Yeah, it's an enamine, right? Okay, what's the relationship between that enamine and the one I showed?
That one's awesome.
They're regioisomers, right? The double bonds in different regions. So the answer is yes, you can have regioisomer. I just showed you one. And I showed you mechanistically. You believe the mechanism? Is it reasonable? Now, which is more likely to be favored? The one I showed or the new one on the right?
Sure.
Why? Because the alkene is more substituted. Less substituted. Just like back when E1 elimination to alkenes. So yes, this can have stereoisomers. It can also have a regioisomer. Regioisomer is a constitutional isomer, but it just, in the context of the reaction, chemistry took place in a different region. What is this drug down here? What does it have in it? It's a drug used to treat fibromyalgia. Not quite sure what that is. I think it's some type of neuro
Basically a bunch of pain.
pain. I think it's real pain, but it's just not chemically something. But lo and behold, what type of functional group is this right here?
Enamine.
Got an enamine in the structure. Yeah?
So,
How would you synthesize that enamine functional group?
You just start with an aldehyde and then you just do the same.
How would you synthesize that?
Start from an aldehyde.
it's gonna be.
Yeah.
Wait, starting from what though?
Aldehyde. Double bond.
That carbonyl plus,
You're missing a carbon.
Oh yeah, you're missing it.
Yeah, you're missing a carbon on that.
No.
yeah, missing the,
Oh, I'm leaving.
like that. Problem is, I'm not sure about this guy. 1, 2, 3. If this could come around here and react, this may have been protected at some point. But we have to sort of ignore this reactivity. But here, because it's an enamine, the double bond's not here. We couldn't put the double bond there. The double bond had to be on the side there. Okay? Now, in the next several reactions we look at, we're going to see imines as sort of intermediates. It's a special type of imines. There's a chemical test that involves essentially an imine, given a special name, hydrazine or hydrazone. And then Mr. Wolf Kishner. Remember we said we'd look at the mechanism a little bit later, or later is now. Wolf Kishner. Please have a safe break.